Hello everyone, myself Anusha NJ. Today I am going to discuss the topic Fundamentals of UV visible spectroscopy, emphasis to EMR spectrum and electromagnetic transition in charge transfer and ligand transfer field. Before going to the topic, let us know some introduction about UV visible spectroscopy. It was believed that light travels in a straight line. Electromagnetic radiation can be described as a wave occurring simultaneously in electrical and magnetic fields, and it can also be described as if it is consisted of particles, that is called as quanta or photons. Wavelength or frequency are used to describe a wave. The wavelength of electromagnetic radiation are expressed in either meters, millimeters, micrometers or nanometers. The radiation may be characterized by its frequency, which is defined as the number of complete angles per second, also called hertz. When visible light is passed through a prism, it split into 7 colors, which correspond to definite wavelengths. This phenomenon is known as the dispersion. And next, come on to electromagnetic spectrum. In electromagnetic spectrum, the wavelength of visible light range from 400 nanometer to 700 nanometer. The visible region, however, is a very small part of the entire electromagnetic spectrum. Visible and ultraviolet radiations cover the wavelength range from 200 to 800 nanometer. The absorption of radiation in this region causes the excitation of pi electron in a conjugated or unconjugated system. Thus, an UV visible spectrum is quite useful for detection of conjugation and carbonyl groups, etc. The infrared radiations cover the wavelength range from 0.8 to 2.5 micron, constitute near infrared region, and that from 15 to 25 micron is called far infrared region. And next one is UV visible spectroscopy. It requires electromagnetic radiation of high energy. The visible region corresponds to 400 to 800 nanometer and UV region is 200 to 400 nanometer. Further division of UV into near UV and far or vacuum UV. On passing electromagnetic radiation in the UV and visible region through a compound with multiple bonds, a portion of light is normally absorbed by the compound. The amount of absorption depends on wavelength of the radiation and structure of the compound. UV is sometimes called as electronic spectroscopy. UV spectrum records the wavelength of absorption maximum and the strength of the absorption. Molar absorptivity is defined by combined Beer-Lambert's law. And next move on to Beer-Lambert's law. Beer's law was stated by August Beer, which states that concentration and absorbance are directly proportional to each other. Lambert's was stated by John Enrich. Lambert stated that absorbance and path length are directly proportional. The Beer-Lambert law states that for a given material sample, path length and concentration of the sample AB directly proportional to the absorption of the light. A is equal to epsilon into LC. A is the amount of light absorbed and epsilon is the molar extinction coefficient and L is the distance covered by light through the solution and C is the concentration of absorbing species. And next one is theory of molecular absorption. The transition from singlet ground state to excited triplet state is symmetry forbidden. The highly probable transition due to absorption of quantized energy involves the promotion of one electron from the highest occupied molecular orbital to the lowest available unfilled molecular orbital. In most of cases, several transitions occur resulting in the formation of several bonds. The next one is types of electronic transitions. According to molecular orbital theory, when a molecule is excited by the absorption of energy, its electrons are promoted from bonding to an antibonding orbitals. The antibonding orbital, which is associated with the excitation of sigma electron, is called sigma star. Antibonding orbital, so sigma to sigma transition orbital, it is represented as sigma to sigma star. When a non-bonding electron n gets promoted to an antibonding sigma orbital, then it represents in n then it represents n sigma star transitions. Similarly, pi to pi star transition represent the promotion of pi electron to an antibonding pi orbital, that is pi star orbital. Similarly, when an electron is promoted to antibonding orbital, it represents n to pi star transition. The energy required for various transition obey the following order: sigma to sigma star is greater than n to sigma star, and n to sigma star is greater than pi to pi star, and pi to pi star is greater than n to sigma star. Next one is sigma to sigma star transitions. It is it is high energy process since sigma bonds are general and very strong. The organic compounds in which the valence shell electrons are involved in the normal UV region, that is 180 to 400 micrometer. For saturated hydrocarbons like methane, propane, etc., absorption occurs near 150 micrometer. And next one is N to sigma star transition. This takes place in saturated compounds containing one heteroatom. N to sigma star transition takes place in saturated compounds and containing one heteroatom with unshared pair of electrons. Some compounds undergoing these type of transitions are halides, alcohols, esters, ethers, aldehydes, ketones, amines, etc. Such transitions require comparatively less than that required for sigma to sigma star transitions. Next one is pi to pi star transition. This occurs in the unsaturated centers of the molecule, that is in compounds containing double or triple bonds, and also in aromatics. The excitation of pi electrons requires smaller energy, and hence transition of this type occurs at longer wavelength. Next one is N to pi star transition. An electron of unshared electron pair on heteroatom gets excited to pi star antibonding orbital. This type of transition requires less amount of energy out of all transition discussed above, and hence occurs at longer wavelength. Next one is chromophores. Chromophores are unsaturated groups responsible for the absorption of UV regions. Example benzene, quinone, etc. Then oxochromes, saturated groups which when added to chromophores cause a shift in the absorption to a longer wavelength and an increased intensity in absorption peak. Next one is bathochromic effect. Bathochromic effect is also called as redshift. A shift of maximum absorption towards longer wavelength. The intensity of epsilon may or may not be changed. This is called as bathochromic effect or redshift. Blue shift or hypsochromic effect. A shift of wavelength towards shorter wavelength without change in the intensity is known as the blue shift or hypsochromic effect. And next one is charge transfer transitions. Charge transfer transition is a very important process being responsible for the intense UV absorption of large number of inorganic and organic species. In order to exhibit a charge transfer transition, it is necessary that one of the component have electron donor characteristic and other have acceptor properties. For example, SCN is better donor than chloride, thus maximum absorption of iron and cyanide complex of chloride is in the UV region charge transfer spectra is obtained by running the spectra of donor and acceptor separately. One addition band is observed which is due to charge transfer transition. And the next one is ligand field transition. Ligand process sigma to sigma star, pi to pi star and non-bonding n molecular orbitals possesses sigma to sigma star, pi to pi star and non-bonding n molecular orbitals. If the ligand molecular orbitals are full, charge transfer may occur from the ligand orbitals to empty or partially filled metal d orbitals. The absorption that arise from the process are called ligand to metal charge transfer bands. Forbidden transition may also take place, giving rise to weak absorptions if the metal is in low lying empty orbitals. A then a metal to ligand charge transfer transition may occur. They are common for coordination compounds having acceptor ligands. Thank you.